Hello, everyone. Welcome to discussion in week 6. Today we will cover some examples in the transform. Okay. So first, we need to know how to calculate the transform. And we know that the expression is x of z equals to m from negative infinity to positive infinity of x of n times z minus n, right? It is a infinite power series. And in lectures, most of the signals we talk about are causal signal, which means that the x of n equals to 0 when our n is negative. Okay, it's a causal signal. So we can further simplify the equation to the sum from 0 to infinity. Okay, and we also need to notice two different signals, x1 of n and x2 of n, might result in the same x of z. So to uniquely define our x of n in the z domain, we need to include ROC as well. So x1 of n and x2 of n can be differentiated. Okay. And how to determine the ROC? So ROC is a range of convergence. If a point z is in the RC, for example, if r equals if z equals to 1 is in the ROC, that means x of z when the absolute value of z equals to 1, it is a finite value. And finite value means it converges. Okay, so these two are equivalent definitions. All right, and we know that the x of z, if it is rational, we can always write it as a ratio of numerator and denominator, right? And we know that we will have two polynomials of z, poly 1, poly 2. Okay, and from the polynomial 2, we can get the poles. And poles are the points that make poly 2 equals to 0, right? So we can see that when the z equals to the value of poles, the poly 2 will be 0 and xz will be infinity. And back to here, we know that when xz equals to infinity, that means it cannot have a finite value, right? So it cannot converge at the position of poles. Therefore, as long as we find the positions of all the poles, we can determine the ROC. If the signal is right side, which means that it is only non-zero when it is bigger than n0, when it is right side, its ROC is always something out of a circle. And if it has multiple poles, the ROC will be out of the outmost pole. Or okay, so we can see that this pole is the farthest away from our origin, so the ROC will be bigger than the most outmost pole. And similar for the left-sided signal. For it, the ROC is always inside some radius, and the poles are outside. So in this case, Z is smaller than the poles innermost. All right, so here are the basic understanding of our Z transform and the ROC. We should make sure that we compute both of them. Okay, any questions up to now? Great. Okay, I find the question. So first, I give an example of x of n in time to me. And here is n equals to 0. Let's compute the Z transform together, and you'll see how easy it is. So we have x of z equals to the infinite sum. Oh, sorry, there's a 3 here. So you see that it is not a causal signal So we have to use from negative infinity to n to plus infinity for our range of n. But you see that the signal itself is finite, right? This is finite. So we know that the x of d is basically a finite number of terms. So it should be, this is 0, this is -1, -2, -3, -4, -5. Okay, so this is x of -5 times z minus -5, so it's 5, and x of 0, z to 0, which is 1. Similarly, we write all the rest. Okay, -1, -2. All right, and we substitute the values inside. Okay, so are we done? No, we still need to determine the ROC, right? And to reveal that, ROC is a range of the magnitude that makes the x of z finite, right? And we notice that the x of z is already a finite sum, right? So theoretically, any z should satisfy the criteria, which means that the z is all the complex numbers. But if we take a closer look at it, we'll see that there is 1 over z here, right? So our z can't be 0, so it should be bigger than 0. And also we notice that there is a term of z, right? So our z itself cannot be infinity as well. Cannot be infinity. So we exclude the infinity as well, and then we get the range of convergence. It should be 0 to infinity, but the two extremes are excluded. Are we done now? Yes.
Wait, a quick question. I'm just curious about like the z like not being equal to infinity. Like, I mean, I think like isn't it mathematically like z would never be equal to infinity anyway? So like, I'm just curious like why would we go through this? Like the way you say it makes it seem like there's a case where z can equal infinity or something like that, or I don't know. Yeah.
So z equals to infinity means that you can take any large number. So so it is like saying you can never imagine how big the number you would take, and in that way, the z the value of x of z will be uncertain, right? It can also be randomly large, and in this case, we cannot say that it converges.
Okay, I think I kind of get it a little bit.
Yeah, and sometimes when we say that e can be equal to infinity, is in the case that we only have constant and 1 over z terms in the x of z. So you'll see that for 1 over z, no matter how big your z takes, it will converge to 0, right? So it doesn't matter. But here we have a z to the 5 term here, so it will be affected by the z equals to infinity this case. Yeah. So
but like if you were to actually like graph it, like isn't z absolute value of z like less than infinity versus like less than and quote unquote like equal to infinity? Like wouldn't that have the same graph or whatever? Like if you were to like draw out the actual region of convergence, or no?
When you draw it, it is difficult to draw. Like because we know if we want to exclude 0, we can simply circle the 0, right? But for infinity, we need to write down, right? Because it is hard to draw that there is a the infinity is excluded.
Okay. Yeah, I get it. Okay, thank you.
Yeah, so it is because it's difficult to draw. Good question. Yeah, and if you review the lecture, you also see a quick conclusion. So the conclusion is when you have non-zero x of n in the negative side, so if you have so if you have non-zero supporting on the left side, you will need to exclude infinity. And if you have non-zero supporting in the positive side, it will exclude 0. So this conclusion is basically derived from our equation, but it can be used as a quick conclusion to check your result. For example, our x of n, you see that there's there's some non-zero values on both left and right side. Okay, so both 0 and infinity are excluded. Okay, and let's continue. So the second x of n is not a list of values. It has its expression. So let's say it's 1/2 to the n when n bigger than 4, and it is 0 when n equals smaller than 3. So you see that it is this signal looks like this. Okay, and this is 4. Nice. So this time it is causal. Right? We know that, okay, it is only non-zero when n bigger than 4, equals or bigger than 4. And then we substitute this, right? And we see that we can actually merge the two terms into one term and apply the geometric sum. Right? And we notice that the n starts from 4. And if we let m equals to, if we let n equals to m plus 4, which means that m equals to m minus 4, we change the subscript, and the m will start from 0 to infinity, right? And then the m becomes m plus 4. And we know that, okay, we have m equals to, n is a variable when 4 is a constant. So we can split the two terms like this, right? And this term is not affected by the sum, which means that it is a common portion of each term. So we can extract it out of the sum to make the summing easier, right? So we will have this, and using the geometric sum equation, we'll get this. All right, and then we put all the z's together. You get the constant is 1/16, and the z to the 4 will become z to the minus 4 in numerator. All right, so we are done with the x of z. And what about the ROC? In the equation, we see that there is only 1/z terms, right? So we don't want z to be 0, and also because the pole is 2, right? No, the pole is 1/2. So when z equals to 1/2, this one is 2, and 1 minus half z2 is 0. Okay, so the pole is this, and then because it is a right-sided sequence, so the range of convergence will be larger than the outmost pole. Okay, so our z bigger than 1/2, and because we have z minus 1 here, we also need to make sure z bigger than 0. Okay, so merge these two together. We only need to write down the first inequality, right? So that is how we come up with the RC of this x of z. Great. And what about this? What about we name the first s of n as x1 of n, and the second as x2 of n? Okay. And now we want to compute the convolution of x1 of n and x2 of n. Any suggestions about how to do that?
Multiplying the z domain?
Yes, exactly. Well, we can always do the conversion time domain, but let's make our life easier. Let's do it in the z domain. You're right. And as we discussed, we already know x1 of z, x2 of z. Okay. And one thing to be careful about is their ROC. So the ROC here should be the intersection of the two ranges. Okay. And for the first one, we know that it is this, and for the second one, we know that it's this. All right. So the result should be between half and infinity. Okay. So you just can't believe how how convenient it is. Any question here? Okay. Oh yes, one more thing is that you know, if you need to convert the x1z times x2z back to the time domain and make so okay, this is a sum and this is a ratio. All right, this one is simple. You just need to times them together, right? But sometimes the x1 of d and x2 of d, they might all be in the rational in the rational forms. So they're both sum, and multiplying them together is very troubleshooting. So we'll prefer the case that it is written in multiply mode. Okay. So this is some trick. So if they're originally in the multiply mode, you just need to put all of them together, right? But let's see. I believe the homework and exams will not give you too much calculation burden. Okay. So let's come to the last questions. Okay. The last question is here. Sorry. Now we want to do the opposite. Any clue? So in the lecture, oh sorry, continue.
I was gonna say, do you need to specify a region of conversion for this, or were you gonna guess that or no?
If it doesn't specify, it means that it is all complex numbers.
Oh, okay.
But wait,
I think
I see. Okay.
I think you mentioned like if it doesn't specify, like assume it's causal or something like that, or I don't know, but I guess that depends on the example.
Yeah. So, well, this is not invented by me. I just noted that in the question they say that the xn is causal. Okay, so the x of n is causal. So yeah, apparently we cannot take xz equals to 0 here. You're right. Sorry. Okay. Well, as long as the sequence has one non-zero value, it seems that we always have constraint there, right? Because unless it's an impulse, right? When it is equal to 0, the z to the 0 minus 0 is always 1, and our x of 0 equals to a constant times 1. Okay, will be equals to x of 0. Okay. We have 3 tricks in the lecture to do the inverse D transform. But the other 2 of them are mainly conceptual methods. The only common practical method is a partial fraction expansion. And it might be easier as we suppose. So we want to break it down into several parts, and the denominator of each part should contain a pole. And we notice that there is a square here. That means there are 2 poles here, right? They are repeating. And in this case, we need to name 2 terms. The first term is 1 minus c to the minus 1. The other term is its square. And so if the repeating times is m, we should have from 1 to the terms to the m, okay? And m is 2 here, so we'll end when it is equals to 2. So this is a general case. All right. So this equation seems intimidating, but they are basically means you need to differentiate this term for several times, and usually in the homework and exams, the m will not be too big. So the most common case is m equals to 2, probably sometimes 3. Okay, and you need to like practice taking the derivative for 1 time or 2 times here. Okay, right, so let's come back to this equation. How to compute the A, B, C here?
So I think A and C are straightforward, right? You just plug in, like, I think Professor had it in class, like you just multiply by like the root, and then, or yeah, you multiply, sorry, by the like the denominator, that specific denominator, and then you like evaluate at Z equals like that specific pole, and then that'll like cancel out everything else.
Yes, great. Yeah, so you're right. So the first pole is 2. In this way, we'll get our A. Thank you for your answer. The A should be 4 here. And similarly for B, B should be -3. And as you said, the C is a little bit different. Okay, so similar for C, but B is a little bit different. So for B, you have to do this. P2 is 1. Okay. And the M is 2 here. So this is basically 1. And this is also the first time differentiator. All right. And you substitute the x of z inside, and you make that z equals to 1. We'll get the result. But if you have very few terms, if you have very few terms in this equation, for example, you only have these 2 terms, and you want to get A and B, and you don't want to get this computation. Another way is to merge them into a term, into one term again, and the equation will contain A and B, right? And then you can align the equation with your original one and get the values of A. Actually, we can also do it for this specific question, okay? And then we want to merge them together again. And then we'll get A times 1 plus B, right? And you split them again, you get an expression in terms of A, B, C, and D. And then we know the numerator should be 1, right? Should be 1. So you get the equation of A and B and C, blah, 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 blah. And maybe, so you know the coefficients of these terms should be 0. And the coefficient terms for z to the -1 should also be 0. And you know the coefficient for the constant term should be 1. In this term, you can also solve the A, B, and C. So you just need to compare which case is easier to compute, and then choose your method. All right. And back to the questions. We know the x of z is in this form. This is actually very neat. And then we just need to convert it back to the time domain by checking a table. Okay, so we know that 1 minus a z, this map to a to the n times un in time domain. Okay, and for the first term, we get 4 of 2 to the n un, right? For the second term, we get -3 times so the a is equal to 1 here, so it should be a constant. And for repeating terms, so by checking the table, this term corresponds to -1 times n u of n. All right, and this is also the properties of the x of z. So when you have an n in your times of n in your time domain, you get a differentiation in your z domain. Okay, and you'll see the differentiation of 1 over z minus 1 will generate you square of it in the denominator, right? Okay, then we convert them together. We have this. Therefore, we get the result in our time domain. Okay, so that's a content for discussion today, and feel free to ask questions. Oh, someone asked questions in the chat box. I mixed it up the case for repeating roots and polynomials. Can I ask what do you mean? So when your poles are distinct, which means that they don't repeat itself, we only need to list them in the order of 1, okay? And if it repeats twice, we need to write down its original form and then the square of it. If the repeating times is m, we need to continuously write this sequence until we have the original form to the m. Okay. And the case for repeating roots and distinct roots are also different when you want to compute the coefficients here. So for the distinct poles, we just need to do this, okay? But when they're repeating, we also need to include the differentiator here. And the number of differentiating depends on how many times it is repeating. Okay, I hope that answers your question, then I will stop recording.